无视问题了，造成你的。
这个桌子上是不是也有扩音器？文字上提问的时候，
也有已经发答案了。
拿不到这个扩音器在。
啊，有，可能是那个
上面有这个东西啊？
哦，那也不是。我要那边前面麦克风，但前排敲桌子听不进来。有听到那边的前排敲桌子。
OK，我们开始上课了。So last time we talked about the graphic theory. We introduced the Lagrange polynomial form. And we derived the spatial motion. We also talked about how to understand the strength to construct the original fundamental theory. The strength is by the locality. Which essentially means the action has to be a single integral. Cannot have double integral model, right? Your Lagrangian density has to be associated with a single point. Okay? It cannot be separated point. That's what we like. Okay. And the last part of last week's lecture, we talked about a very important property of the field theory, even in the classical level without contact, you can see it clearly of symmetry. And we proved the famous another theorem. So those theorem says that if there is a continuous local symmetry is G, then there should be associated conserved current. Okay, G mu. G mu has to say this part mu. Zero is conserved. Okay? And we clearly see J mu has a simple form. Okay? The two parts. If you still remember that the one part is coming from the variation of the Lagrangian, another part is coming from the symmetry constraint. Okay, which is come from the photo derivative of the Lagrangian. Then we can get this J mu. This is a very general result, a very important result. And we also mentioned there's with this J mu we can have a conserved charge, okay, which is basically the space integral of zero component with current, okay. The simple form. Later in today's lecture, we will very soon see this is an important operator. Because without quantizing, you can view everything. It's not an operator, right? It's not yet an operator. But after quantization, the field becomes the operators. Okay? Or this J0 and Q become the operators. Okay? So this is a space integral. This is of course, a functional space. Okay? So after quantization, record this J0 is a local operator. Okay? Local operator means there's something inserted somewhere. Okay, that's what we mean by local operator. And then by definition, this Q is a non-local operator, right? You see, if you put the local operator and do integral, you see. So Q is a non-local operator. So what is the dimension of Q? I view Q is some operator, but this is at this moment is just some the name, okay? But even before quantization, you can see in this way. For example, J0x is the local function, right? And you do integral, then you get Q. Okay. So what is the dimension of this Q? Q has dimension of the order space. You see. Right? Because it's integral of x, right? So if your space is three-dimensional, then Q is three-dimensional. You see? Is that clear? I mean, the Jx is some local thing. Local means zero-dimensional, okay? Zero-dimensional. Then you put the zero-dimensional object. You do some integral over x, depending on x, the dimension of your space, okay? Then the object structure will have the same dimension. So Q has a total dimension of the space dimension, right? For example, in 3 plus 1 dimension, 0 Q has dimension 3, E equal to 3. Okay? Is that clear? Because Q is constructed like this in this way, okay? By definition. So Q has dimension 3. In more fancy language, the dimension is using the codimension. You know what is codimension? Does anybody know what is codimension? Does anybody don't know what is codimension? Codimension. Codimension means I have a total space as a total dimension. Okay. And if I count the dimension of my object, I will just count the difference. Okay. Difference with this total dimension. Okay. So in this 3 plus 1 dimension, if your object is 3 dimension, we can also call with codimension 1. Is that okay? Because 4 minus 3 is 1. Okay? This is the codimension. So the point is, question? The point is in any dimension, this conserved charge has a codimension 1. Okay? It doesn't matter you're working on 3 plus 1, 2 plus 1, 1 plus 1. Okay? The dimension of this Q is always codimension 1. It's very trivial fact, right? Because this is always the integral over all the space. It has to be codimension 1, right? because the remaining dimension is time. Okay, in time, always dimension. Okay. So this is the important part. In the modern language, to understand the symmetry. So later we will see this lecture. After quantization, we can always construct a four-dimensional one operator for any continuous, for any global symmetry, any symmetry. Okay. So since this is important, let's spend a few more minutes to discuss the theorem. The theorem says, first of all, it says whenever there is a continuous symmetry, there is associated conserved current. And in deriving this conservation of this current, it's clearly we have to impose the equation motion, something like that. Okay. We have to impose the equation motion, otherwise you cannot get this conserved current. And discrete symmetry. If you are a curious person, you immediately ask. You're right. You always now emphasize the symmetry has to be continuous. And what happened for the discrete symmetry? Okay. So for discrete symmetry, we don't have conserved current. But is that all? Then we just forgot all the discrete symmetry is useless? Of course not. Okay. Discrete symmetry is important symmetries. Okay. Discrete symmetries are important symmetries. Then what? The point is you don't have a associated conserved current. By current, we just mean this local function or local operator J. Okay. Instead of that, you might still have this conserved charge. Okay, that's the point. So, but we don't have, but we still have conserved charge. Okay, or sometimes they will call this just a four-dimensional function. Four-dimensional. It still have that kind of object, which is a cube, right? To discuss the cube. Cube is a four-dimensional operator. Okay, with the integral over the whole space. Yeah, this is a very hot topic actually in research-wise recent years. I actually work with a few students, including undergraduate students. We're still working on this. Okay, it's just under development. There are many new stuff recent years to understand new types of symmetries, very new type, different new discovered symmetries. For example, if you relax this four-dimensional one condition, if you want to allow yourself to go to four-dimension 2 or four-dimension 3, for example, four-dimension P, then you have some more fancy new symmetries or higher form symmetries. And if you relax yourself, you don't want to restrict yourself to this group property of this symmetry. At this moment, we are always talk about symmetry. We talk about some example from the group theory, right? Okay. For instance, this continuous symmetry is always a Lie group. Okay. And the discrete symmetry is a simple discrete group, finite group. Okay. Always the group theory. But if you allow yourself to go beyond the group theory, you still want to try to construct something very much like the symmetry. And also a new research topic in recent years discussed a lot. We can recall this is the non-invertible symmetry. Invertible symmetry is the group theory type symmetry. And if you want to go beyond it, non-invertible symmetry. Okay, these are always very interesting topics. So in case some of you are interested in doing some research, you can follow this direction. So because of the equation motion is important that we're going to emphasize the current is conserved only on shell. Yeah, this is our traditional language in field theory. We sometimes record on shell, off shell. If you don't know it before, then let me explain. It just means on shell means you with imposing this equation motion. On shell means you have to impose equation motion. Equation motion satisfied or imposed, we call it on shell condition. Okay. Okay. If you don't do that, then we call off shell. Okay. Off shell. Off shell means not necessary to impose equation motion. Your field equation motion basically constrains which kind of field configuration can be allowed, right? Right? That's what equation motion does, right? Equation motion tells you how the field has to evolve, right? In space-time, right? Then you can impose it or without imposing it. If you impose it, we call it on shell. If you go beyond this, we call it off shell. Okay? It's just terminology. We have to get used to this terminology to understand these things. So the current is conserved on shell, which means the equation motion is satisfied. And the last point is I already explained quite a bit. Is the modern viewpoint of the symmetry. Is by some co-dimension 1 or 2 or p co-dimensional non-local operators. Okay, basically the conserved charge. Okay? This is basically the conserved charge. So we use that conserved charge or construct those conserved charges to implement or to define my symmetry, basically. That's the modern viewpoint to understand those symmetries, right? This is still, up to now, is not included in any textbook because it's just modern materials. In case you're interested in okay, so the main topic today we're going to try to address is quantized fields. And then after quantization, we'll come back to discuss this symmetry again, okay? After that, then clearly all those Q or J are operators, okay? You can talk about how these operators commute with other operators, what's the physical meaning of that, how to write explicitly using these operators to manifest the symmetry transformation, okay? Onto some other operators, okay? Because as I said, as introduced last time, we're always focused on how to transform a given object, okay? Send it to some other, okay? Then how to make this is very precise using these operators. Yeah, we're going to come back in the end. But before that, let's try to address how to quantize the fields. And for this purpose, let's again back to these harmonic oscillators. Which I guess you are all very familiar with. Actually, there's a homework, especially with the chain of harmonic oscillators. So, in the experience of quantize these harmonic oscillators in quantum mechanics, we already learned at the very beginning, the first lecture. We know the easiest way to do it is just to promote the equation of motion, classic equation of motion to an operator equation. Okay? Then find the solution and then promote this integration constant to operators. Okay? Those operators are basically the creation and elimination operators. And then we use these operators act on the vacuum, which defined by Q, which defined by Q and some A operators. Then we can build up all the states in the Hilbert space. Then we're done. Okay, very easy, right? So what we did with harmonic oscillators basically to promote this XT with an operator XT. Okay? Some operator XT. Then immediately the equation of motion becomes some operator equation. Right? When you find the solution, or promote the classic solution into an operator solution. The classic solution is something like this. As I said in the very beginning, when we want to promote this to an operator solution, all these omega parameters in the T. Even in quantum mechanics, we know T cannot be built as an operator, or we often don't do that. Some people try to push in that way. Okay, and I think it's a traditional way to understand time is not an operator. There's no way to put the object on an operator. Is to try to promote the integration constant as an operator. So we put the A hat. A star becomes the A hat dagger. That's the way we quantize this one. And we have the P. We also have this P is defined as M function P X. Then we got both expressions for X and the P in terms of A and A dagger. Okay? And you can easily check the standard canonical quantization condition between X and the P now becomes the commutator between A and A dagger. Okay? A and A dagger. This is the so-called quantization condition. This implies A and A dagger is 1. Okay. Then if we define a vacuum by A here, vacuum, then we can build up a excited state so-called in the Hilbert space, where I just add a dagger many times along the vacuum. Then these are all the states. Then basically you are done. Then we streamline this procedure to quantize my harmonic oscillator. And you can extract the steps of quantization. Way. So first, we promote the equation motion to operate the equation. And then find the general solution to equation motion. You might think that this might be redundant because everybody knows that. Because quantizer field is essentially every step follow this quantization of harmonic oscillator. So let's be very clear. Okay, streamline the procedures. So find the most general solutions. Solution to what? To equation motion. And then promote integration constant. Really, nowhere else you can promote. The only thing you can promote is promote the integration constant. Integration constant in this second result, two constant operators. Okay. And then impose, don't forget this one, then impose the quantization condition. Last step is using these constant operators to fuse the Hilbert space. Okay, 5 steps. If you do one by one, you should be able to quantize the field. Now let's do it. So first we have to write down the equation motion. So let's do the simplest example, which is the free field, free scalar field. Real scale. So the equation motion is the simply just as the box I equals 0, right? This is the equation motion. To write this explicitly, this is a partial t squared minus x derivative squared x minus 5 equals 0. Okay. Second step, we have to find the most general solution to this equation motion. This comes back to your second year undergraduate course, mathematical physics, mathematical physics. How to solve this equation? This is a partial differential equation, right? Okay. In order to solve a partial differential equation, how to do it? Can anybody say something? How to solve this PDE?
Separation.
Yes.
Variable separation.
Okay. Sure. Yes, that's one way. But for this one, I think it is even straightforward. Okay, let's do it this way. As he suggested, we can do some separation. But for this one, we can move one step forward. Okay, one can just try some particular solution and then make the solution most general. Okay, that's also one way, right? So, how what? You can try something like an APT times E to the E focus. This one, right? Right. This is basically says that I just try to Fourier decompose a general solution, okay, in this space direction. I do a Fourier decomposition, and then I retain this T-dependent part, and then make this as some index. So this actually the P. There's a P dependence. We fancy this one. So in this way, the T dependence and X dependence are also separated, right? So this is some kind of ansatz, right? We can view this or some special solution, potential special solution. Okay. The point is you can plug it into and try to solve and find some solution. So let's do it. Let's try this one. Try this plug in this original equation motion. Then what do we get? What do we get? We will get a partial T square plus P dot P, which is centered in P log square. T equal to 0. Okay? See? Then you immediately realize, okay, the reason why I choose this way is what? It's because this equation motion is a harmonic oscillator equation motion, you see? Right? This is precisely the harmonic oscillator equation motion. Okay? And this one is just X. And this total thing is just omega squared. Right? You see? Then this is the harmonic oscillator equation motion. Maybe this is more precisely, this is nothing but X double dot plus omega squared X equals 0. Okay? This is the harmonic oscillator equation motion. These two equations are the same. Okay? This already suggests at this moment you should view P is an index. Okay? Okay? Different P just to label different harmonic oscillators. You see it? See? Because of this fact. Okay? It's the same. It's the same. So I can change my P, then I get different each. When it's for each P, you get a harmonic oscillator. Because you get an analog to this X. See? That means for each different P, you get a harmonic oscillator. Okay? And then P is a continuous parameter. Because P is continuous parameter, then which means you get infinite harmonic oscillator. Okay. In this P space, right? So that's the lesson here. And as promised, we want to find the most general solution. We are not only satisfied by this observation, but we want to find some most general solution. Then you realize a general solution is phi xt. Then this is for a particular P. Right? From the very beginning, the plug into some special solution with the fixed P. Okay? You can immediately check. You can combine you can combine this kind of solution for different P together in the form of a general solution. And make it precise, I can write this combination because P is a continuous parameter, just an integral over P space. So I realize that APT I P plus X plus AP star P minus I P. This is still the solution. This is also the solution. Okay. Okay. The previous one is just some piece. Now I write this most general form. I split it into these two pieces for the same reason like what we did no, in harmonic oscillator case in t direction. Right? Remember that the two pieces and the coefficients are complex conjugated with each other in order to make sure the impact function is real. Okay. Okay. Otherwise, you are not sure whether it's real. Okay. In this way, it's guaranteed to be real, right? Okay. So this is the most general solution with this Fourier decomposition. Of course, there should be further constraints for this one. These are not the arbitrary solutions. Okay? Not the arbitrary functions. There has to be some constraints for this APT. Okay? Because this decomposition only solve the x direction. Okay, how the x direction solution is going to be, but does not yet touch the t. And as already explored there, the APT has to satisfy this more solution. Right? So let's solve it. Let's solve the APT. As said, APT and the APT star are conjugated. So if I solve this one, then since this is enough, okay? Okay. Then let's try to find the solution for APT because the solution is a harmonic oscillator solution. And then plug it into this one. Okay. Then I really get this most general solution in some explicit form. Okay. Everything is explicit. What I mean is, let's solve this. Let's solve this one. How to solve it? You already know, right? When you solve it, there are two pieces, right? Minus I omega t and plus I omega t, right? Because that's the harmonic oscillator equation motion, the same. Okay? Then you get two pieces. Then you plug into this one, then you can form a solution in an elegant way. So for this one can simplify the above equation. In the above equation, these are the unknowns. Then you can write after solve this one, you can write this phi xt in an elegant way. Okay. Then you will get the AP. Okay. AP is some constant without the t dependence. There is a t dependence, but pointed I solve it out. So I get AP e to the minus I p dot x. Okay. If I don't put this symbol vector, this symbol here, this usually means this is forward. Okay. Okay. This means forward. P dot x. So it's the forward vector in Cuban times. I just combine everything together. Promoted to the four-dimensional space. Then I get AP star e to the I x. That's what it is. So it's emphasized that here this P dot x is the inner product. For a full vector. For example, mu should be equal to omega and C. Okay? So from here, you already know here, in order to make analogy with harmonic oscillator, we have to define omega equals to omega squared is the P long squared. Okay? This is my definition of omega. So, which means what? Which means omega and P are not independent. Okay? Okay? Omega and P are not independent. Okay, so it's very good. So where am I now? I'm just finished to find the most general solution for my fields, right? So I'm at step number 2. Okay, I'm just at step number 2. What is it left? Last we have to promote the integration constant operators. You see. So let's do it. So how to do this promotion? For sure, it's very similar to the harmonic oscillator, right? Let's try to find, in this most general solution, which object can be promoted to operators, okay? For sure, not this one, okay? Okay, because we know, from the very beginning, conceptually, it's very clear. In field theory, we have to view the field as operators, not x or t, okay? X and t are just labeling index, okay? The field is operator, okay? So not this one, and of course not this one. So the only place we can promote to the operators is this AP and AP stuff, okay? Very similar to the harmonic oscillator, right? If you want, the only complicated thing is here, we put some additional index P, okay? And then make all these piece of solutions, combine them together. Because this is the integral, okay? Integral means sum, okay? You sum all these different P modes together. But the point is, for each P, is really precisely the harmonic oscillator, okay? You see it? It's really the harmonic oscillator. Okay, then let's do it. So promote this to the operators. So in this promotion, so from here, we extract some coefficient factor in front for later convenience. Okay. For instance, here I put the 1 over square root of 2 m omega. Okay. This is just normalization. It's not a big deal. Okay. It's just a normalization for some convenience. Okay. We're also going to do the same thing. So let's promote. Then I put a hat. Then this is the operator. Then this can be written. And with some free factors here. Okay. See, this is also an omega. Yeah, I don't have that. I need some math, but in my case, in this moment, I will, for simplicity, I will consider m equal to 0. Okay. Later, I will mention for m non-zero case, what will happen. Okay. Then I will have AP hat e to the minus e plus AP dagger hat e to the and dx. That's what it is. Yeah. So as mentioned already above, p dot x here is omega t minus, and omega is the log of t. Not independent. This is the solution after this promotion. See, I finished the step number 3. Do you have any question? Yes.
就我想问一个问题，就是关于那个频率欧米伽，它为什么这里它没有写它对那个 p 有依赖？因为在解那个 a 的那个方程的时候，
I emphasize independent. You can make a more clear equation. That's fine.
Oh, okay.
That's fine. That's better. I don't find it a big deal. Yeah. This means they are really not independent. Yeah, maybe this is better. You can do it this way here. Any other question? That's the definition of omega. Omega is defined as the log of p. Coming from the energy to the oscillators. Okay. Another question.
就是它那个是 phi 在那个是那 hat 那边为什么它会多？那个是多一项，那个是根号一下2欧米伽 p。
It's just normalization factors.
微好。
So later you will see this is pretty much convenient and it's good. So it's a good normalization. It's a good normalization.
我问一下，就是取那个叫什么弦认子解的时候，是不是取到这个解是为了让它做一个洛伦兹不变量？
No, at this moment we cannot see because they are not the physical quantities. This is just the operator. Okay? We cannot talk about the Lorentz invariance.
APT 它解的时候应该是
You know, for Lorentz invariance we have to talk about the physical quantities. Some overlap of states and some proper distance, all those are physical quantities.
如果平常按照数学上面解的话，那个 APT 它不止就是怎么说，可以取到其他的地方。就是它可以取到一个欧米伽 t 和一个半欧米伽 t 的一个线性组合嘛。但是这样的话，它限制在是 APT 是 AP 乘以1的 i 欧米伽8欧米伽 t。然后在这一层的话，我能想到它需要在后面组成一个论述变的，也就是说上面是一个负的 p 乘以 x。
No, we will see soon. This factor indeed is relevant to Lorentz invariance, but not at this stage. Don't confuse. Later we will see it very soon. Yeah. Just later we will use this operator because these operators we are trying to focus on. Okay. We think those operators create something. That something is might be physical. Okay. So when we use this operator to create some state, when we measure the log of the state, which is quite a physical quantity, you can see this kind of normalization indeed guarantee the Lorentz invariance, but not at this stage. At this stage you cannot see it. Any other question? It's a very good question. Okay, then let's continue. Because this is still step number 3, we have to finish it. So we come to the core of this quantization, right? Everybody learned in quantum mechanics, the quantization condition are extremely important. Now, how to improve the quantization condition? Let's okay. Now this has to be we have to understand them first and then impose the proper quantization condition. As said, each mode before impose quantization conditions to use the analysis. Each mode with a given p is a simple harmonic oscillator. Okay, and we already introduced the annihilation and the creation operator for each p. That's already p. We already introduced. AP and AP dagger for each p. Then we make an analogy to this harmonic oscillator where the quantization condition in the last stage in terms of A and A dagger is this way, right? The A dagger commutator equals 1. And then you ask, what is the proper quantization condition for the fields? Okay. Then the answer for the proper quantization condition, making an analogy to this one is, okay, in this case with the p indices. With this p indices, because p is a continuous parameter, okay, it's a continuous space. P space is continuous space. Now, previously, when you don't have such indices, you have a single harmonic oscillator, you have A dagger commutator equals to 1, okay? Now, what happens if you consider infinite amount of harmonic oscillators, or you assign a continuum indices for this A dagger? Then the analogy of that, of this condition, is the AK. Let's use K. K is the some P. AK AP dagger equals so essentially we use the dirt function. Okay, we use the dirt function because we are now staying in a continuous P space. Use the dirt function. And of course, for others, these are just trivial. A commutator and A dagger commutator are always 0. Okay. Okay. So why delta function? Then you may still ask for some person. I'm not satisfied. Give the answer. Why we have to arrive at the delta function? Well, we know delta function means some density, right? Right. Which means some a local density at some point. If the total integral is 1, right? That's what we define delta function. Remember that? Okay. Delta function means that when you do the integral, you get 1, right? But locally, it looks like a peak. That's what delta function. So in this sense, you can also consider, because if K or P space is a continuous space. It's a continuous space. Instead to search for right-hand side of some 1, you have to search for some density. Okay? Some density in this P space in the right-hand side, which is essentially the delta function. This condition can be more seriously justified again using this lattice picture. Okay, we learned from the very beginning. Just take a lattice. If you don't worry about some confusion happens in this continuous field theory, then you go to the lattice and take continuum limit. You can justify yourself. Because once you go to the lattice, everything is the same. The metabolic quantum mechanics. Just follow learning quantum mechanics way. You can justify this.
2派三次方程，3我知道这应该就只是个单纯的定义问题，但是 这样子不是就会导致我们每加一次 a 大概你要让它那个你那个粒子态，我要再多除一个2派，根号2派34。
No, not so simple. We'll discuss it in great detail. It doesn't mean okay. Okay. So to answer your question, in field theory, if I act using this operator, it's not the same physical meaning as in quantum mechanics you act with. No, it's different. We're going to discuss. So any question about this quantization condition? Is this quantization condition clear? Apparently, there is another way to justify why this is the correct or proper one, right? What is that? Because in harmonic oscillators, you can talk about AA dagger, you can also talk about the X commune with P, right? What is the XP quantization condition? In this case, you can do the same thing, you see? Yeah. I can translate this kind of quantization condition to the XP quantization condition. Is that clear? Why? Because this equation essentially tells how to translate forth and back. Okay. Okay. You can use A and A dagger in order to do that. Phi is also operator, A dagger operators. Okay. So you should view this equation really as the operator definition of phi. Okay. 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 As mentioned in the first lecture, the essential goal to quantize the field is we have to eventually promote all this field from a function to operators, right? Then you ask, what is that operator? How you define properly that operator meaning of that phi? Now I'm telling you, this is the definition, almost, okay? This is almost the definition of phi operator. You should view the phi operator defined in this way, in terms of A and A dagger. Of course, you can also try to understand the A and dagger in terms of phi. Force in the back. What I mean is, this quantization condition, you can work with, you can also formulate another one. If I like the equivalent. Equivalent to, let's say phi. Let's say phi is also operator. So I can talk, if it's the operator, I can talk about the commutators, right? So phi and phi x prime t this kind of commutator. Then you using this kind of quantization condition, you can immediately justify it. Is that correct? Because this is just the equivalent form, right? Just compute this one and plug in the operator definition of phi using this AA dagger commutation relation. You can easily do it. Which means this quantization condition and this quantization condition are equal. Okay, they're just equal. This is a sample exercise, but you should check it. Let me make some important points, remarks. So we observed that for these phi, pi, or phi pi commutation relations or quantization conditions, these operators are all located at equal time. So this is sometimes called equal time commutators. Equal time commutators. which is very canonical, right? Because in canonical quantization, we really view time is very special, okay? Okay? This is what we call the canonical quantization, okay? Not some other path integral looks more covariant. So what is pi? Yeah, I hope you still remember. We defined pi in the classic field discussion, right? Because pi is the part of P, pi. Also very similar to harmonic oscillators. So this is pi. And because the phi definition of phi is here, then you can work out the pi. So pi is I minus I integral you see this factor appears, this factor is very similar to the harmonic oscillator P. I used it already, but I have the factor here. And then the piece find AP. One piece is the AP dagger. This is my pi, okay? So pi is the conjugate variable or conjugate operator for phi. And the equal time commutators for phi, and phi pi are given in the AA diagram notation relation. And both are the promotion of this single harmonic oscillators, okay? In this kind of condition. So where are we now? We essentially finished the prepare. We finished the step 4. There's another step, okay. Another step is to build the Hilbert space. It's not trivial, by the way. I'm just telling you the result, but you should check it. Okay. Not a trivial fact. They're just equation. You should work it out. You should work it. So let's continue. So how to build up the Hilbert space if all this can be done? This comes to the question someone asked. So, in order to build up the Hilbert space, clearly we have to act this A dagger on the vacuum, okay? You see? But the question is, you act this A dagger or AP dagger onto vacuum, you get some state. What's the physical interpretation of that state? It's the question. So let's try to understand it. The answer for that question is the AP dagger act on vacuum, create a particle, okay? Create a particle. Then you ask, how do you know? Well, I can check the state, the property of that state. I can measure this quantity, that quantity for that state. Okay, eventually I convince myself, okay, this state looks very much like a particle state. Okay. Remember that in quantum mechanics, you don't have such an interpretation. You see? Why? Because in quantum mechanics, you only have a single harmonic oscillator. You see? Okay? So when you act once a dagger, what's the physical meaning of that? Sometimes we use some confusing terminology, right? Some M particle or whatever, but it's not precise. It's not accurate. In quantum mechanics, you don't create any new particle, okay? Okay, you just increase your energy by a unit amount. That's it. Okay? That's the accurate way. Okay. Because from the very beginning in quantum mechanics, we fix the number of the particles. Okay. We don't create any new particles. Okay. So that's the difference. That's the difference. So what's that? So to build my Hilbert space, H, curly H, okay, we act AP dagger on vacuum state. Constant. Like before, the vacuum state is defined to be over here by AP or any P. Any P, okay? The vacuum state is defined here by AP or any P. That's my vacuum state. Then I can act AP dagger times, okay? You can imagine you have a lot of choice, you see? Now, because P now came up with new indices, okay? You can act many times for a given single P, okay? That's fine, right? Because for each P, you have a harmonic oscillator, that's the point. You can also choose different P, okay? P1, P2, P3. You can also do for each different P, you act at different times, whatever you want, okay? Like that, because P is a new index. So we're going to justify, as I said, we're going to justify more clearly how AP act on a vacuum state, how to understand that physical property of that state, that created state, okay? But at this moment, let's accept it and try to structure the Hilbert space, understand the Hilbert space. So if you agree, this AP dagger acts on vacuum state to create a particle with momentum P. Then you can define the for given momentum P, you can define the number of particles, right? Depends on how many times you create. Okay. The point is you act once, you create a particle. You act twice, you create two particles. You can choose you create two particles. One has momentum P1, another has momentum P2. Perfectly fine. We have that picture. Imagine you are working in this P space, okay? You can create as many particles as you want. Each of them can have different momentum or coincident momentum. The same momentum is perfectly fine. So with that in mind, essentially we can structure my Hilbert space in terms of small n, where this small n is essentially the number of my particles. Okay. You see, imagine a Hilbert space. Imagine a Hilbert space. The Hilbert space can be decomposed into the different sectors. Okay, each sector associated with a number of the particles, small n, which means this curly Hn is some space. It's some space, or it's include all the possible states created in this way. Okay, P1 to Pn. P1 to Pn. Act on the vacuum state. This P1 to Pn can be the same or can be different. Doesn't matter. Okay, as I said. The point is this n times means n parts. Yeah, sometimes we call this entire space as the Fock space. It's just a lane. It's not a big deal. And clearly, currently Hn are the n part second. So as emphasized, this interpretation for the state created by the AP diagram is quite different from quantum mechanics. Yeah. Please keep in mind. They are not the same as quantum mechanics interpretation. Do you have any question about the Hilbert space? The Hilbert space we constructed in the last step, we quantized the fields, free fields.
这个我想问一下，这个希尔伯特空间的完备性怎么说明？就你构建的这个希尔伯特空间的完备性怎么说明
Where are you? Okay. Yeah, I think you can check it.
How to check it?
Because in this case, it's trivial. Because it's a free theory. Free theory means all this particle state just don't touch each other. There's no interaction. No interaction means there's no exchange of energies or whatever. Okay. Okay. Whenever you have two states, just pass through each. Don't touch each other. So yeah, there's no subtlety. Everything's there almost. So if you run in this way, all the possible state, you get what it is. Yeah. You don't have any two states combined and form another new state. Something. Everything's trivial. Because we are working in free theory, right? We're working in the free theory. Any other question?
The vacuum state as a concrete formula.
Concrete
formula.
You mean which is as a concrete formula?
写的跟那个差不多。
Sorry, I'm writing what Hilbert space? Sorry, I didn't get the first one.
就是说这个 vacuum state 是不是一个
You mean one particle state? One particle state? Yeah, we're going to continue to discuss this maybe after the break. Yeah, that's a very good question. Later, we'll talk a little more about this normalization issue, where we realize that the state we're now talking about are very, very ideal state. Okay, in other words, the plane wave type. Okay, which does not have a finite normalization. Okay, in that sense, you might say this is not quite physical. Not quite physical, but there's a way to make it physical. For instance, we can construct a very physical wave package by dressing some functions. Because within the knowledge of this P space, all these states, we can try to combine them using some package function. Okay. Then after doing this P integral, we can in the X space we can really have some very physical state without any problem. Mass, this was maybe already very rigorous mathematics. Here we don't discuss much about this physical normalization. Make everything simple. Okay, that's very good. Any other questions? Okay, maybe we can have a break. 15 minutes. We'll continue the break.
我知道H1那个是到那个前阵子他那一个，因为他这个谜题是第一个例子的话，我也记得他或者是指标加一个，或者是那个
幕报，它就是正处的一维塔那个，那到底其实会写吗？就是它，我觉得就是你会去验证你把那个A 单个给它弄到一个真态上，然后你把它和那个总量算，会发现它只是你的预测，单的东西大一点，还有是你认为它的物理意义是那个原因 A 单和它
这两边那个是。
如果你是用这种场算符，按符就能搞正风的场，
这个就两个平板之间差一点。
这样子的话，你应该是可以得到一个 x 上的德尔塔的。
那就如果真的把
那个我认为德尔塔，那个场上相当于它确定位置上是一个例子。
它会变得比这个更强。哦，变得空间这个没有这个派并流。这题有正常的吗？算的都是。有说正常的这个，因为我就证了他哪有
对呀，它有就是好像是完备的记忆的，它第二题的最后问法，第二题对，我也是就写了个正交归一，我在考试说像这些词肯定是完备的，
对，
完备吧？
那就不理论上叫什么减真怎么证？我得说你们其实太准。
是，为什么要把它们？会谈都是那些不同的吹风太有关系。我理解是，
那你是不会就是题目都不会，
他肯定不会说
有小的地方大概像着人。
首先太丑了。
没有我讨厌。我那个这个两个，就床好像压那个，就它挺多一点，就肯定不会这一些没有意见，可以用讲就确实就以后会有那个都是用感觉。你看，加2的
加上算符的就可以
看一个反正有这个情多，就说给一个有但是给你记为王督导，那哦，对。 目标，然后自然会完全就不会跟这种配置这样的形式，但是反正把原子就是把正常开的地方开成那个流体这个地方，就是多来一个小的带然后一个到一个你把这个方式理解它跟有些人就是像这个像那个我的学生就会用这打和它有一个名字小的那个
哦，
这个
节庆日，所谓节庆日，这个
对，它会。
它
那种，如果你看到你工作，记住是 follow 原始的，快没有从你上去里边，你看它等于都证明了它哦，我最近总做的这个，感觉它是后面提的。
你增加完备，你不能代表是全部了吗？加一个那个修的，
我这个是算它的
说的
对，确实。
那我要是没挣这3个，我就直接说他3个就结束了。
那得看他说的是这个，
要不就是我自己先做一半。
而且这个太麻烦了。
我对上来。
对啊，
就自己也露出。
但这个
还不如直接就认为它我觉得这里面就
然后它
不是说啊，我透到时候也是直接就认为那个要全部留在等于一样，我没有证据，
证据考虑
这是一个成熟的体系了，有什么
如果能揪出它的本身函数，那它一定是没解法。
对啊。
然后
叫什么？这都多少年前的东西了，相信数学家的教育。
产物上面然后可以
人家也没正常别
对，
积分又没有，积分也没严格定，然后积分还是
积分我一直搞不懂，
那个叫我只会 limit n 去积分，就那个 n 个积分号 n 一个写法。
我真的不知道他是怎么，就是那个 h 趋近于0的时候，他是怎么做到的？当然可以唯一到那个，就是怎么做到
退化到经典，
退化到经典形式。
那个其实就是本身它那个就费曼也本身就挺恐的，就是因为你那个 h 趋近于0了之后，它那个
正当确实很厉害，
然后我们就直接认为他们 cancel 掉了。
我们凭什么 cancel 掉？我操！
因为都是高频的语嘛，这个相当于可以认为它可能相当于某种卷积，然后它这个和在高频部分是很低的，然后所以高频就全部被 cancel 掉了，
这太神秘了，
大口不压就行。
我看的时候差点被忽悠去学电竞联系的。
反正物理意义比确就行。
不是他这个退化真的看不懂。啊，对，基本上只有形式上的问题那玩意儿。
对，有些是。
你加一下，
再加一个。
你说对，我记得我是先为什么？
我也先问错啊。你是老的。对的呀。
因为我之前
是把它 export。然后再录。
不像高中把它给发。
不小，而且这个所以能正化分解。一般其实很多人解一个可以靠 J B G 带也可以去就他不把那如果一个人多解的题，那如果都举记过去一次一次，确实会知道过。
这个我自己就
别求了，
很多的图都是多。哦，见闻嘛，这种。
So we just finished finish the quantization of the prefields. Yeah, there are many details. I hope you can check some claims, some small calculation. You have to do it. Otherwise, you don't have any feeling about what happened here. Okay, you have to check it. Yeah, perhaps I can do some text for you. For example, this one, did you already check yourself how to prove this one? Also this? And also for this non-trivial implementation relations. And there are a few questions about how to understand the state in the Hilbert space in a more precise way. We're going to discuss this right now, okay? And there are a few more others. So let's put them together, give the remark for the quantization procedure. So this whole procedure. Also, about massive. Okay. So as mentioned, for massive scalar, then omega is defined in a different way. Omega, let's put now omega p. Omega, for the massive case, this will be the p squared plus m squared. Okay. Right. And the equation motion of the scalar now becomes box plus m squared on phi. So in principle, okay, so in principle, you can do the quantization procedure for this new equation motion once again, but it's not necessary. You don't need to do that. The point is, if you replace the previous omega with this omega p, then everything works. Okay. It's a massive series, also a free series, essentially the same, with a new defined omega. Okay. With a new defined everything we talked about before is still true. So another thing is about the Hamiltonian itself. Okay, remember that when we discuss the harmonical oscillators after quantization, we can even write this Hamiltonian, right? Remember that, and measure the Hamiltonian or energy for a given state. Because once you build up your hyperspace, meaning you know what are the states look like, then you can measure physical quantity for those states, right? The first important physical quantity is the energy, right? So you can measure the energy for a given state, for example. Here we can do the same thing. You can do the same thing because we already finished the quantization of these free fields. We have our hyperspace. Now, suppose I want to measure the energy for some given state. What should I do? You should first work it out. What is the energy operator, right? So in quantum mechanics, every physical quantity associated with an operator. So what is the energy operator? It's Hamiltonian, right? It's Hamiltonian. Now the point is, in classical field theory, we work out many quantities like Hamiltonian, right? Momentum, whatever. Now switch to after you already quantize the fields. Now the correct way to say it is all these are operators, right? You should view all these, including Hamiltonian itself, as operators. Okay. Right? We know Hamiltonian is also formed by pi and phi. We know how to express pi and phi in terms of A and A diagram. So we basically know everything. So you know how to understand this Hamiltonian operator. In principle, you can calculate. You can act this Hamiltonian operator for a given state. You can measure the energy. Okay. So what you can do. Okay. So just remind yourself. So in classical field theory, we already derived this one. This curly H is distinguished from this hyperspace. Don't be confused. Okay. Using something. Computer notation. So it's the Hamiltonian density integral over the space. See? Okay. We know what is the Hamiltonian density, right? This is what we already worked out in the classical field theory. Just look back. You'll note. Then this is half pi squared plus half relative pi squared plus half m squared pi squared. Okay. See? So now the point. The point is we know all these are in terms of as operators, right? Because we know phi hat. Just promote everything to operate. Okay. And in particular, phi is the part of T phi. So you can plug in the AA Geiger expression for pi and phi into this formula. Work it out. Is that clear? You can work it out, right? Because we know what is pi and what is phi. So you just plug in and work it out. So I can express H in terms of a diagram. In this case, it will be the AP and the AP diagram. AP diagram. Okay. The AP diagram. So what is that? Then you get, after a short calculation, then you get H is the integral over P omega P AP dagger AP plus up AP commutator with AP dagger. So simple, right? You see? Get a very simple expression here. So here we use notation AP or AP. There's no time dependence for AP or AP dagger, you see? Because AP and AP dagger are promoted from the constant, integration constant, right? Which has no time dependence. Remember that? We factorize out, we separate out the time dependence, right? Into the P dot X, okay? As 4 vectors, okay? So all this AP and AP dagger there's no time dependence, okay? Is that clear? Now you see something magic happen. Once you arrived at this result for H, previously H is some integral over some look complicated operator. Right? This operator including phi and pi. In principle, phi is a function of both x and t. You see? Right? So all these phi or pi has some time dependence, right? In the beginning, okay? But afterwards, after we do this combination or calculation of this whole thing, following the definition of Hamiltonian, eventually you will arrive at something has no time dependence. You see it? Okay? Because AP dagger doesn't have a time dependence. You see it? Does anybody know the reason? Why my Hamiltonian operator has no time dependence? Yes? No interaction? No, that's not the reason. Any other? Who said it? You? Oh, that's right. Because it's a conserved quantity. Okay? It's a conserved quantity. It's a conserved quantity. Okay? When your system has time translation invariance, you should have energy conserved. Okay? Indeed, this theory has a time translation invariance. So I should be able to get, I should have a conserved Hamiltonian, which means there's no time dependence. Or you can say all this seemingly time dependence has to be cancelled afterwards, eventually. So that's the reason. We have a very nice result for this H, which means we can do something, right? we can measure this operator or energy operator for some given state as problems. But before that, let's look into some details about the second term. So, because we have the second term in this way, it looks we can further calculate. We can move one step further because there's a commutator here. In principle, I have all the commutation relation. I should be able to calculate this one, right? Right? So what is this one? Can you calculate this term? 1 minute. Try to calculate it. It's very interesting calculation. Because I already told you all this commutation relation. You should be able to calculate it. 1 minute. Calculate it yourself. Okay. Does anybody know the result? Got the result? It's not super difficult. It's very easy. What is that?
Infinity.
Infinity. What? Which kind of infinity? What is that? No, I'm asking this only the second term. What is the result? What did you get? That's something. How to calculate this? AP commutator with AP diagram. It's already here, right? It's here, right? Everyone knows the result. Look, I tell you generally KP, how to commutator. Now I just said K equals to P, right? What is the result for K equals to P? K equals to P.
Zero.
Means 0, right? But don't forget, this is which space? This is momentum space. Okay? This third function is defined in momentum space. Okay? This three-dimensional third function defined in momentum space. So what is the result for this delta 0 in momentum space? That's the question. What is that? Can anybody know? Does anybody know the answer? I almost tell you the answer, but last step is important. What I said is we already know from here that obtained is the AP diagram commutator should be some 2 pi qubit delta 0. Okay, delta 0 means the K space. Okay, delta 0 or K equals 0. K equals 0. Okay, so what is this? This is the momentum space of delta 0. What is that? You know? What is delta 0 in momentum space? What?
那是一个单位点，然后
You can see
E 的 I IXP。
Yes, and then and
就是体育的 XP。
yes.
我就把它在当下那方式做一个那个复列表。
Okay, what's the result? One definition for delta function is what? Is e the IPX integral x. Okay. Now you set p equals to 0. What is that?
just e 的 x 3 e 然后
That's right.
x1 是
dx。
It's just the pure space integral. The result is the pure space integral, and then physically, what does it mean? The volume. Okay. So volume is a more accurate answer compared with infinity. It is infinite, but it's a volume. Okay. It's a volume. Okay. So this is the volume. This is the volume. So we can, after understanding this, then I can simply replace this community because this is the volume. This is the volume. Now we can do something more interesting. For example, we can measure the energy for given state. Okay. And what's the simplest state? Of course, the vacuum. Okay. So we can first measure the vacuum energy. Or the vacuum energy density, if I mean this stage. Let me clarify each one coding. One vacuum energy. Yeah. So I can measure this and divide by V, which means I measure the energy density. Okay. This one is the total energy, and this is volume. Okay. Energy divided by volume means energy density. Right? Because I know the operative definition for this H in terms of A and A diagram. Okay. I know how all these operators act on the vacuum. Okay. We just compute it. Okay. Compute it. We do the calculation. And what is it? What is the result? Because vacuum was cleared by A, right? Vacuum was cleared by V, by A. So the first term disappeared. See, you get 0. You only have a second term. And you divide by the volume. So what do you get? You got this one, omega p divided by 2. Okay. Very simple. And what is this? Don't forget your omega p. What is the omega p? Some p squared plus m squared. See? Look at familiar integral. Do you know how to do this integral? Very familiar integral, right? That's the answer. You have to perform this integral. That's the answer. So what is the result from this integral? This is the infinity, right? Of course, because the integral diverges. But what's the basic meaning of this result? Usually, once you get some result, you have to try to interpret it, right? You have to try to interpret it. Now I'm trying to measure the ground state, which is the noise energy state, supposed to be. I measure the energy density, means that I measure the energy at every point, okay? At every point. but the result tends to be still is the infinite amount. Okay, that's the result, the infinite amount. So you might say, okay, who cares? By definition, ground state has to carry the lowest energy. Okay, it's the lowest energy state. Then why don't you just throw it away, even though there's infinity? That's one terminology. You can do it. You can choose it to do it that way. Okay, basically, which means that for any other state, if I want to talk about the energy for that state, I basically measure that energy compared with this noise energy state energy. Okay, only relative energy matters. Okay. Okay, so in that sense, you can try to subtract. So you can define energy above the ground state. Okay. Then mathematically, it doesn't mean you throw away the second term. You see, is that true? That ground state energy only comes from the second term. You see, if I only measure the energy compared relatively to the ground state energy, then it means that I can throw away the second term. Okay? Which means my new Hamiltonian now becomes omega p. AP dagger AP. Okay, only this term. Okay. And this is my relative energy operator. Okay, this is my relative energy. Some other observation also you see, only the first term has the explicit operator meaning because it has a dagger A. The second term is a constant. If you only focus on the second term, it's just a constant piece. Okay, it's not an operator, or you can view this as a trivial operator. It's some constant times the identity operator. Okay, does not do anything. Okay? In hyperspace, it's just like a constant. You can move, vectorize times whatever you can do. So with this new H, you can check basically interesting relation. For example, you can try to calculate the H commutated with the AP daggers. So when you compute this H, commute with the AP dagger, you will get omega p AP dagger. Okay? Okay? This roughly means what? This H commute with some operator can be viewed as you measure the energy. Okay? Okay? Measure the energy. You see, if you get some looks like some eigenvalue times or some number constant times the AP dagger. Okay, you see? Did you learn that in your quantum mechanics? Right? Sometimes, right? You want to measure some energy of that operator, then you just make H commute with that. See what you get. Okay, see what you get. If you're lucky, you get some constant times that operator, which essentially means the operator carries this amount of energy. Okay. Of course, if you insist, serious person say, what do you mean by a operator carries some amount of energy? Looks ill-defined. That actually means you act this operator onto some state, for example, ground state. Okay. Then you create some new state, right? But the point is, what is the energy of that new state? Or what is the extra energy once you act this operator you create? That energy actually means that kind of energy. Okay? But roughly, you can view it this way. Okay? some energy, some operator carries some amount of energy, but actual meaning of that is what I said. Okay? You can also measure H commute with the AP on the AP dagger. You get minus omega p AP. Means what? Means this is an annihilation operator. It's decreased energy, right? One is increased energy, another is decreased energy. Okay? Decreased by how much amount? Is this omega p? Precisely this omega p. Okay? This in some sense justifies another statement which we mentioned earlier. AP dagger act on ground state. You get created a particle, okay, with momentum p. You see here, because you increase the energy by omega p amount, right? Which means if you measure that particle state, you will get the omega p as your energy. Then you know that state carries a momentum p, right? Which means you precisely get a single particle energy momentum relation for that state you created, right? Because a priori you don't know which kind of physical meaning for the state you created. The only thing you can do is I just try to measure this quantity, measure that quantity, see what happens. Okay. Now if you do that, then the calculation result tells you that okay, I know that the new state carries momentum p and the energy omega p. Okay, then I can convince myself, okay, this state is really a single particle state. Okay, that's the way to find the physical meaning of this state you created. Okay, in your Hilbert space. So, like this, one can also construct or study the momentum operator. As said, both the energy and the momentum now becomes operators because we quantize everything. Okay, quantize everything. So what is the momentum operator? In classical field theory, you already know your momentum given by this interval. I think that we have special. Right? And see the vector. Again, now you have to promote this as an operator. You know I and you know phi, just plug in. Okay. So you work out what is your momentum operator in this kind of relation. Then what you get is the P integral, your P and the AP diagram. AP, very similar to this one. Okay, here is the omega P, AP diagram AP. There is the P, AP diagram AP. Okay. Now you can check with this AP, then you can check the ground state of P. So what's this? This means what? It gave me a state. I try to measure this physical quantity, right? This means now I measure the ground state momentum. Okay. So if this is given by this, then what is the result of this one? Here, right? Here the ground state, right? There. Perfectly makes sense, right? It just means ground state does not carry any total momentum. Okay? Ground state does not carry total momentum. Now, as already mentioned, the one particle state. One particle state was given by you act one state factor on vacuum. Okay. And for normalization reason, let me put 2 omega square root in front. Okay. Okay. And define this as my single particle or one particle state. This way. As said, this is a funny factor here to make sure the normalization or law is Lorentz invariant. Somebody asked earlier why there's sometimes there's a fancy square root 2 omega or 1 over 2 omega in front. From here you can see if you put this without put this you might not get a Lorentz invariant law, but with this you get a Lorentz invariant law. Okay. You can check yourself. It's a very interesting exercise in this lecture. For example, one fact you can try to convince yourself is many times we use this kind of 3 momentum integral, right? 3 momentum integral. Now, one very interesting fact you can check yourself is this is not Lorentz invariant for sure. It's only some subspace integral, okay, in the entire Minkowski space, right? So one fact you can check is this combined with 1 over or times 1 over 2 omega p. It's indeed Lorentz invariant. Okay. Okay. This is a very interesting fact. You can check. Even though it's a 3 momentum integral. Okay, but it's Lorentz invariant. It takes a few minutes to check. Here is the same. You can check. One can take the long. This p overlap with itself. Okay, you can get something more in the environment. But it's not a big deal. It's just some normalization factor. As that, how do I know such kind of state can be interpreted as a one particle state? Okay, a priori we don't know. Okay, but we can check it. You can measure physical quantities. You can measure physical quantities. Once you measure the physical quantities, you can convince yourself that state indeed carries. The state carries momentum p and also energy omega p. Okay. Also energy omega p. How do I know? Well, again, I already handed you the state explicitly. Okay, this is the explicit state. If you want to measure either momentum or energy, so act the effort. Act your h or this p operator onto this state. See what happens, what you get. Okay, that means you measure this quantity for this state. And you can convince yourself. You get the momentum p and the energy omega p. Okay, then this looks very much like a p momentum particle state. Because in the relativistic case, if a relativistic particle has momentum p, it has to carry the energy omega p. Okay. So after that check, I know, okay, this is indeed a one particle state, and it's different from the quantum mechanics. Higher energy state, right? It's really a single particle state. Then you can do a lot of checks in this way. You can try to check a 2 particle. I can create twice, right? I can have AP dagger, AP1 dagger, and AP2 dagger. I have 2 particle state. Okay, I can have 2 particle state. For example, P1 and P2. Okay, I can have 2 particle state. Then I can also check the energy and momentum for the 2 particle state. Then you realize that the energy of the 2 particle state is omega P1 plus omega P2. Okay, and the momentum for this two particle state is p1 plus p2. Okay. Then you realize that okay, this is really a two particle state because they pass through this check. Someone asked earlier a very interesting question. How to make here all the states to be more physical. Okay. And that's a very interesting question. As you can see, when I say this is a p momentum particle state, it's really like in quantum mechanics, or you learn already, it's like a plane wave type. Okay. Okay. It's lost some local state. It's lost some local state. It's really a plane wave state. In that sense, looks not very local, physical, because of the normalization. It's not finite. Right? Normalization is not finite. But you can use this many p state. You can combine this p state to form a more physical way, like we package type dimension. Yeah, that's something we should pay attention to. Okay, maybe we should continue both of them. Yeah, for example, let's discuss this in more detail. So what do I mean by that? Let's try to look at, we introduced this single particle area momentum state, P state. We can also try to think about then if you're a naive person, maybe even when you read the quantum field theory chapter 1, first a few pages or any textbook, you might ask yourself, you are saying everybody's saying that the field has to be promoted to operators, right? So we should means phi is an operator, right? Then you can ask a very, very naive question. It's actually an important question. What is the state? What is the state by acting phi x on the vacuum? Right? That's the very first question you can ask, right? Right? You are now I was telling you some, switching some momentum space, okay, to explain things. I can also insist in this way, right? Because now phi is already an operator, right? Once you have an operator, you can act on the vacuum, okay? Always, okay, you can do that. Now questions you can ask, what is the state you get by doing this way, okay? I don't like p momentum, p space. I like x space, okay? So I can act phi x, because phi x is an operator on the vacuum. So what is the state you can produce? That's the question. Do you have any idea how to understand this? It's not a big deal because in the very beginning we introduced the operator definition of the phi. Phi here is phi x, you see, xt. Okay. Now the problem I have to do is I act this one onto the vacuum. Because I know, the point is I know this is in terms of A and A diagram. So the problem transformed to how A and A diagram act on the vacuum. Afterwards, do some linear combination in the P space, you see? Right? Because integral over P in the P space linear combination. This means to answer this question, the only thing I need to do is I plug into the operator definition for phi x. Okay. Then what I get? If I don't split x and t, this x means the 4 vector. Okay. Space-time location. What I get? I get phi x act on the vacuum essentially I just add those two terms. And one term is A, another is A dagger. I know A here, the vacuum, I threw it away. Only leftover thing is the A dagger. So I get the P integral 1/2 omega P E I omega P G now I D X from P state. Okay? And just a minute ago, I know AP dagger I can with one state, I get P state, right? Right? With some new normalization factor, you can use the P state to express my phi state, my phi x state. Okay. This is what I get. So try to understand this. What is this? We just try to convince UP in some single particle state to carry momentum P. Okay. You see? That is this single particle state. Now with this factor and this measure, it just do some combination, some particular combination this way, right? Right? This is a linear combination because integral is a sum. Okay. This means a lot of P state combined together, linear superposition. Okay. Okay. Quantum mechanical language. You do a superposition in this way. Or more physically, you can think about it. There are many different P, like a plane wave state, but you put this state together. You put this state together, and you form some state looks like a more local, because this state somehow surround this X point in the space. Okay, position space. Okay. Intuitively, you can think about, okay, when I act 5x on my vacuum, I create some excitation at x, right? At x. Then if somebody asks you which kind of excitation you are talking about, then you tell them this right-hand side formula. Okay, this is the precise way to construct this excitation localized at x. Okay. That excitation can be decomposed in P space, into this P state. And you can also think about the P state combined together form this local excitation. Okay, hopefully this is clear. You can also do one step further. You can try to project. You can project this state that you obtained onto some broad state which carry a K momentum. Okay, you carry a K momentum. You can calculate this one. Anyway, the lesson is you can do. I'm telling you all the tricks. You can do any calculation you want. Okay, at this stage, to justify yourself which state you obtain. Okay, you just check many things. For example, you can check this overlap. This means I want to understand this state. Now I project this state onto some on K state. Okay, to try to understand what I get. Okay, depends on the result, right? Then after a few minutes calculation, it's not that difficult because this essentially means this. There's a K here. Now there's the integral P varies omega P, and there's a P. Yeah, if you want, I just write down everything. Recently, there's the AP dagger. Right on the vacuum. See? And then you just calculate it. Okay, and the first term here, the vacuum, only the second term remained. Now, second term, we calculated using the commutators. Using the A diagram, using this A diagram. Can I erase it? Using this A diagram, efficient relation. The P in A, plug in, then you catch the result. This result is nothing but the E I omega K T minus I K X. Okay. This is the result you get. So what is this? This is nothing but the extension of I K to X for vectors. Okay? See? This is the plane wave amplitude. Okay? You see? This is the plane wave amplitude. Is E is I K dot X. What does this remind you? I'm just now showing this exercise, trying to remind you what you learned before in quantum mechanics. In quantum mechanics, you also have a X state and a P state, if you remember that. Okay. X state means my particular position eigenstate, right? Position space eigenstate means my particle really located sharply at X, okay? Not Y, okay? Just only at X. Okay? Position eigenstate in quantum mechanics. Now you also have P state in quantum mechanics. The point is when you take overlap of X state and P state in quantum mechanics, you get this same result, okay? Now I'm working in field theory, it's completely different framework, okay? I'm trying to make an analogy with quantum mechanics to help you to understand which kind of state you obtain. And I want to understand this kind of state. I take the state overlap with some K state. I get this result very similar to the in quantum mechanics. You take an overlap with the P state and the X state, if you remember, okay? In quantum mechanics. Now, I conclude this phi X atom vacuum looks like in quantum mechanics some X state. Okay, that's my conclusion. But be careful, they're not the same. Okay, if you spend a few seconds to think about this analogy, you realize that they're not the same conceptually. Why? Because in quantum mechanics, if your particle is located at X, it really means located at X because it's the position eigenstate. Okay, nowhere else, which means X state and Y state are orthogonal. Okay, no overlap. Okay, but in field theory, it's not true. Okay, you can check. You can check this state with some overlap with some other state, for example, phi hat Y. Okay, you can check this. You see? Okay, it's not zero. Okay, which means in field theory, you can intuitively think about a phi X atom vacuum state really excited something local at X. That's fine. Okay, but the point is this is not sharply orthogonal to other position excitations. Okay, the overlap is not zero. That's topic we're going to calculate next time. By the way, next lecture is going to happen, I don't know, according to the schedule. It's in Sunday. Do you want to continue on Sunday or? So we're going to continue. We're going to do the next lecture on Sunday. Yes. So everybody is going to come on Sunday here, same time. Okay, fine. So we're going to continue. So next time we are going to check this one. We realize this is not zero. Okay, that's what I try to explain. Distinguish from quantum mechanics. So that's the conclusion. Conclusion is I don't know this. The conclusion is phi x atom the vacuum is similar to x state in quantum mechanics, but not the same. Not the same. Okay, be precise. And as I said, responding to the earlier question, from here we can also get some message. You can insert some functions to dress, to deform or address, for example, some other functions as a function of p, some fp, for example. Here. Okay, to deform or to define a new shape, how you linear combine with this p state, right? Then you might get something associated with this f. On the left-hand side, looks like some wave package. Might not be a phi x excitation, but maybe something else because you deform. You introduce some shape function. Yeah, you can also do that as you like. Yeah. Yeah, that kind of trick can guarantee you get a physical or finite law of this state, right? So we learn in quantum mechanics, it's better to have a finite law because law means the total probability. Okay, as a short physics meaning, the probability you find the total probability. So we have like 10 minutes. So do you have any question about how to understand the states we excited in the Hilbert state?
没有很明白，这里这个根号2欧米伽，它这个为什么把这个引入了？它这个就是罗氏不变呀？Yeah.
This you have to check. Take a log again. Log of the state. PO level is P. What would you get? Can you calculate that?
就是
The point is that one is Lorentz invariant enforce you introduce such factor. If you don't do so, it's not Lorentz invariant. Usually we think log is more physical quantity. Some overlap.
我自己和自己内接，然后它出来就是一个分布的变。
2 omega times some delta. Okay.
对。
That's Lorentz invariant. You can prove it. Any other question? Okay, we promised in the beginning of today's lecture, we're going to come back to discuss this conserved operator. Okay, let's do that. Because we quantized everything. Now you can safely say, okay, basically I can view everything as operators. Okay, so including those conserved current and charge. So conserved charge, once again, conserved charge. Now this is for sure should be viewed as operators. Okay, these are the operators. They are the operators. That's the point. Okay, this is very important. These are the operators. So if this is the operators, we actually saw somewhere already here. See, I already introduced for this kind of relation how to move forward. Let's do it in a more systematic way. If this is the operator, for example, your H, which is the Hamiltonian operator, I can try to calculate the commutator, right? Because it's operator, right? Always, right? It's operator. I can try to calculate the commutator. If it's not an operator, it's not, we are not allowed to do so. Okay? I can try to calculate H. I know H is my Hamiltonian, is the conserved charge associated with the time translation. Okay, I can try to calculate the H commute with phi. Basically, you can talk about the H commute with any other operator. So what about in particular for phi, with phi? So H commute with phi, what you get? You can check yourself, right? You know H, firstly you know phi, okay? And you know the commutator among all these AA diagrams, so you know everything. You can easily work it out, the result. What is the result? Let me tell you, it's minus I partial T phi. Okay, this is what you get. It's a very simple result, okay? But there is a deep physical meaning for this equation. You understand this equation? This equation means what? This equation means what? That's right. Right, that's right. This equation almost can tell you how H generates time evolution. Can you see? You see how H, not very manifest by the way, but almost. Okay, we'll see how to make it more manifest. So why this? Why this is not some particular coincidence or whatever. It's actually a very general phenomenon. Okay, this H means that so conserved charge. This means that conserved charge is equal to generator. Even though we didn't really introduce to you guys what is the generator. Let's accept this. Then it really means a generator. Okay. Generator can be defined in the Lie group. Okay. What do we mean by generator? Usually, generator means you have a Lie group. Okay. Because the Lie group is always continuous. Okay. Then in order to understand any finite element of this group or finite object, I can focus on someone near the identity. Okay. We actually learned this when we introduced the Lorentz group. That's the same thing. So generator essentially means those objects which generate this small amount of group. What do we mean by generator? Okay. So conserved charge is actually a generator through this equation. You can think in that way. Now, my point is this is very, very universal in a sense. You can prove, one can prove, I suggest you to prove, okay, the following thing. You can prove following theory. For any conserved charge in the CQ, okay? For any conserved charge, if you act this charge on some phi, remember that when we prove the other theorem, we use some elementary field phi, or phi A if you want, okay? A bunch of fields, right? We first define the half symmetry, transform this phi, and then derive there must exist a conserved charge, which is Q, right? So here, everything is general, okay? That's not restricted to some particular symmetry for any. The point is that whenever you have a conserved charge Q, you try to commute with HA, it will generate some deformation or transformations. Okay. Remember this delta phi A? We introduced in the infinitesimal transformation step. Okay. We introduced this delta phi A. So essentially, the physical meaning of delta phi A is small transformation, okay, or the deformation of phi a, right, with some other small parameter which I threw it away, okay. So this delta phi a essentially means the transformation of phi a. So this equation essentially means Q is the generator. You see, Q generates the transformation over phi a. You can prove this, by the way, for any, just following the same terminology of Löder's theorem. Because Löder's theorem doesn't care any particular symmetry, it works for any. And you can try to use the formula for Q, which I derived last time for you, and then you calculate this one, you realize this is the deformation of phi a. Maybe this is a little bit abstract if this is the first time you see this generator with deformations. But anyway, let me make it more concrete. So another way to see this, why this is a generator, as of this funny line, is to make this equation more concrete. Okay, just the equation is first of all, this equation is about some operators, right? And there is a differential partial t. So it means this is the differential equation, right? Right? Usually differential equation is not so manifest. But you can try to solve it or integrate it, okay? So what is the solution for this equation? Wherever we are given some differential equation, we should try to find a solution. What is the solution for this? Can you guess the solution for this differential equation? Does anybody know the solution? Yes. That's right. There's obviously a solution. Let's try to find the solution. The solution is this is the solution, okay? This is the solution of the above equation. You can check yourself. I'm not cheating, it's really a solution, okay? Now look at the solution. The solution right hand side looks a little bit complicated. Now you're telling me, okay, what are you doing? H is an operator, I have an exponential, I don't know, blah, blah. It's very complicated. Don't be scared, okay? It's just the exponential of some operator. There's a canonical way to do it, to define it, okay? Because expansion, define the expansion using Taylor expansion, for example, okay? Taylor expansion, there are many, there could be many commutators. But just do it, okay? It's just operators. Every step is can be canonically defined, okay? Now check yourself. This is really a solution satisfied the above equation. Now let's look at this second one. This equation is more intuitive. Look, right? What this equation means? This equation means if you gave me a local operator phi x located at t equals to 0 time, right? T equals to 0 times x, okay? Located, inserted there. If I want to get another operator located at time t, I can evolve my initial local operator in this way, okay? So this 2p is basically the unitary evolution of a given operator. You see, this is very, very intuitive. This means this 2p as an operator act on this one precisely does the job to evolve this local operator at the t equals 0 to t equals t. You see? This really means time evolution. You see? I always talk about in quantum mechanics, time evolution or translation, whatever the symmetry transformation has to be implemented by unitary operators. This is the explicit form, okay? You see? This is the explicit form. And also, this is very, very general in quantum mechanics, even in quantum mechanics. Now, I'm telling you in field theory the same. Okay? So if I want to see clearly how the symmetry transformation acts on some local operator, you can always use this one. You can always use a unitary operator. You look at these are unitary operators, right? Because H is a Hermitian, right? H is a Hermitian, which means this is unitary, okay? So these are the unitary operators that act on this given operator. Does the job to transform this one to some other, okay? This is a very, very sounds complicated, right? And think about it for a few seconds. You can promote this one into a four momentum language. Let's use p dot x 50 e to the minus ip of x. Okay. So I use the four vector here. Essentially means space and time can be treated equally. Okay. You can evolve from in a long time direction from 0 to some finite. You also translate in x direction, okay, from the origin to some other. And the operator does the time evolution is the Hamiltonian, and the operator does the space translation is the momentum. That's it. So I form them together to form a four vector. That's what it is. Okay. Do you have any question about this? You should have some questions. For instance, this form is a finite transformation. You can see, okay? This is a finite transformation. However, this is the same as only touch the infinitesimal, okay? Infinitesimal. So when you plug in this solution to check whether this is correct or not, you have to do an infinitesimal expansion, right? It's more parameter expansion, okay? So this, in some sense, this carries more information than this one. This is a finite transformation, okay? It's a finite transformation. Okay, so what I'm telling you that this is a very, very general pattern for to transform a given operator in a sense for any symmetry transformation. Doesn't matter which. For any symmetry, for given symmetry, say G, okay? You can define some U operator is associated with some finite parameter alpha, for example. U alpha, in this case, alpha is this T, okay? This T, and U alpha is this kind of operator, okay? This kind of operator. You can always do this and say, given operator O, I want to create some X. Then if you want to transform some given local operator, you can always do this U alpha dagger U alpha. This means this defines how you transform this given OX. Okay? Or in our familiar language, the symmetry transformation essentially means we send the OX to this one. Okay? This is true for any symmetry transformation. And the control charge occurs in the exponential, which means this U alpha is defined as exponential I alpha controlling charge. See, this is also very general. For any given symmetry, once you have the conserving charge, so now we can see how the symmetry transformation acts on the given object very, very precisely. Interactive. Okay, let's stop. So, reminder, next time we're going to meet at Sunday, same time, same place, Sunday, right?
作业都是现场就对。
现在是那时候，我这里有没有？我在这边比那边我这个还得花，这边东西到你说这好吃，它变了，特别新的，好，特别是太
但是思维的话也需要
有讲基本的那个话，那还是在那个想法里。
因为他在这个16分钟还有
那只是对数字还有一个情况，
慢慢就一个 x 没有那个变化，变化之后还是这个样子。
阿尔法带生出来的话，那就是
几变的这个把出来差有点变了。我感觉
就生出来的话，应该是有另外的一个小的个事儿。
这个对，这个是
比如说平面性。
感觉嘛，
因此那种安稳的，
就是说那个
PX 的一个铁质，所以它的一个就是这个有长那个东西，有长，或者说是 P 三号 generator， 是的，然后我还有一个这个就讲这种零不变的东西，所以它的原理是选，
它平不变性，所以 P 是它的你要平不变性，
是不是？
现在吧。
想问那个的时候是一个这个问题，
最高能量好像是2分之1。
啊，这里面真的有两个解释啊，
它就相当于
而说我要把它写的这个样子，就是如果在日历上带我带一个生物学电池的话，我给它反应半天，我们这个就是电波像这个关系好像是。就是这样的是同样的相是吧？如果再问没有这个的话，是不是要这个问题？是不是有一个这个？
没有这样子，
对，就是没有这样的啊。给我要求它那个动量空间的体的那个地方
啊，
在上面这边对，这是为什么开始我觉得就已经这个思想化的了。你看这个，就上面这个没问题，到底两个都要大的对，因为那个表达方式是要对是那个所以它是要展开，把前面这么反提进来，然后那个2+3次方抵消，所以后面地方展开应该是体积乘以欧米伽 p， 前没有积分了，这是一嘛，所以就相当于是体积，然后所以你下一步这个地方，这个的话，你这里不能再对欧米伽 p 做积，就是个欧米伽 p， 再乘个这个 v 位指标，所以你就要
它没有这个按这个我们匹配，
因为你积分用来算这个 v， 你这里只是两个。
但我觉得这个是很不离意的，它这应该对应的是它的这个
最上面最上面这个对 v 上对当数码题到这来，所以两个那基本上就一，
因为我会因为算是这样
就是一个
如果那样
这一样
话，就是说，
你知道这个 idea 吗？这个 idea，因为因为这个可以换成一个
要你那就能出来，你不出来就出来就
它这个题就是你的
你就出了 v 之后，肯定
然后
一个什么，就有一个积分表，有一个什么。
这里是个1，如果说在里面，如果它这边 p 和 q 是不等的，如果后面是个 p0的话，那是基本上就是1，但是它是这样的，所以它相当于直接换成之后对比积分啊，对吧？这方不应该有积分，那这方不应该是无穷。
对，就相当于把这几张图的全这个东西要把它给它
对啊，还有问一下，那个前面是 constant 的那个 entity 的时候。前面这步做完，你算这个项目体之后，不应当是这个用到。
它可以通过，它就是相当于它的链是，
它这个基本上所以后面可以这样算这个项目，不应该有个机会，应该是
那 v is inside p，
就是你说
v 跟 p 不是一样的，
这是那个什么
v 就来一个多少零，
是一个那个
里面还没清楚多少零，就这个问题吗？
对，
关键是德尔塔零是我们从 physics 的德尔塔零，
不是有两个，
你知道德尔塔函数可以写成积分的 e to the ip，
把这个
没问题的，你们学会方法就是
可以跟你最高码头上它这个，
就是说你因为它只能只要
我用这个来定义这个，
我认为这个的话是为了保
但是很容易验证，当 p 等于0的时候，这个等于什么？这个等于一个空的积分，这个就是 v，你看。
那如果用内核一的，
也
是德尔塔林自己做上来，OK，
这个是一，
的话，
那不是矛盾。
但是 momentum space 的德尔塔林
哦，
，clear，这很简单。
就是我还是不理解这一东西是怎么算的。
啊，这就直接算出来了。
就第一项是零，然后第二项直接
对啊
这个 P。
对吧？因为第一项 Q 叫真空的，就这样有个 AP 在右边，
对，
哦，
所以第一项扔掉了，不算第二项，第二项就直接带进去，有利于这个东西 ，XP 这个除掉。
哦。